Nice. So sorting and insertion algorithms in particular are going to be focused on something that's going to be important regarding how you go about organizing your data in particular. And you may want to figure out, okay, how do you go about sorting things in a particular manner? What's going to be your fastest way of sorting them? If you need to use sorting for particular types of data, which are going to be the most advantageous ones and so forth. Those sort of questions you may ask, so you're going to have to end up learning different sorting algorithms. So there's going to be the most popular sorting algorithms that you will be learning about here in this particular lecture, and then next week's lecture we will have the other sorting algorithms, because we can't do all of these in one session. And we want to see where each one of them is going to be advantageous and disadvantageous in certain situations. So if we're given in some sort of situation where we have an array of person objects and we have to sort this in an increasing order of age, we need to figure out what's going to be a very effective way of how we're going about sorting this. And just from this situation alone, we know that's going to be a very large array. And if we are sorting based on age, that means the range of the ages are going to be in a very small range. And just from watching these two pieces of information, we can select a sorting algorithm that will be best suited for this. So I'm going to give you guys each one of these sorting algorithms, and there are some example code for these posted up on my learner as well, so you can actually get started using them in particular. But at the end of this particular lecture and the other lecture for sorting and searching, figure out which algorithm is going to be the best for this particular situation. And let's see if you actually can get the right answer. I'm giving you guys a hint that the runtime being the best algorithm for this particular situation will end up being O of n. So these 6 sorting algorithms consistently appear throughout any programming that you may do, and in interviews and assessments, you will always be assessed on any one of these 6 sorting algorithms. So insertion, selection, and bubble have been traditionally the most popular, but as sorting algorithms got even more popular and the need for efficiency grew, merge sort, quick sort, and bucket sort became the new popular ones that you need to. But it is still required that you need to learn insertion, selection, and bubble because they are advantageous for certain types of situations. So for today, we're going to be looking at insertion, selection, and bubble sorts. And then next week, we will look at merge, quick, and bucket. So we're starting with insertion, and basically, insertion sort uses what we refer to as a sublist, and this sublist is sorted, and as each sublist is sorted as we keep on going, it eventually ends up sorting the entire array accordingly. So it'll start such that it will start with like, okay, you can start with the first 2 values and sort these, or the first 3 values and sort these, and so forth, and keep on going. And until all the values in the array are sorted in order, then it just goes about just keep on repeating the sorting as of such until it achieves this condition. Insertion sort is not suitable for large data. This is for like if you have a really small data set and you want it to be done in a very quick and efficient manner. The average and worst case complexity for insertion sort is going to end up being O of n squared, meaning that you will end up iterating through the array and its contents of the array twice. So in these particular examples, I'm going to give you guys a step-by-step illustration example as to how each sorting algorithm actually operates. So if we start with our unsorted array here, where we have 8 values and 8 numerical values here, the insertion sort will compare the first 2 values here. And between these first 2 values here shaded in blue, it determines if the leftmost value is less than the rightmost value here. So if 14 is less than 33, 14 remains in the sublist here, shaded in green. If not, 33 will end up being the value here, that will be in the sublist, and then 14 will just be on the other side of all. So in this case, 14 was less than 33, so 14 remains in the sublist here. It then moves on to the next two values accordingly. So it compares 33 to 27, and it sees 33 here is more than 27. So then it just swaps these two values here, so that 27 will be on the left-hand side, and 33 here will be on the right-hand side. So the sorted list here, when it does this swap, it checks the sorted list here to make sure that the items in the sublist is also sorted accordingly. So the sorted sublist only had 14, and the value of 27 that we just swapped there is greater than 14. So we make sure that it remains in that particular order as we keep on going. The next step is that we'll compare 33 with 10 here for the remainder of the array. And then it sees 33 here is greater than 10, so it swaps this. And then we have 14, 27, and 10. It then compares the sublist here, which is all green shaded, and it sees, okay, 27 and 10 here are not in order, so it does the swap here in the sublist. So it goes 14, 10, 27, and it compares the next two values here in the sublist, and it sees it's not in order, so okay, it swaps these two, and it goes 10, 14, 27. It then compares again, and it sees, okay, in our sublist here, it's in order, so we can then go on to the next two values here accordingly in the remainder of our array. And the process keeps on repeating itself until all the unsorted values are basically covered into the sorted sublist. So the steps of the algorithm is basically listed out here, and this is just for your review. But you had the physical illustration indicating how it actually is physically done step by step. The code here for insertion sorts is actually given on the slide here, and it's also uploaded on My Learning for easy accessibility and so forth. Now this code is not the best written code. There is a way to optimize this code even further. And the reason why I'm going to give this point here for thinking about how you can do this, this is some work that you actually may want to think about. And if you do this early, it'll give you a particular advantage for something later on. Right. So any particular questions on insertion sort? Alright, doesn't seem like we have any questions on insertion sort. Alright, so let's move on to selection sort. So selection sort is where we end up dividing the list into two parts, where the left hand side of the list is going to be the sorted part, and the unsorted part is going to be the right hand side of the list. And we populate the sorted part, but starting with the unsorted part of the entire list, and we just keep on filling the sorted part until we actually end up sorting the entire list. So it normally starts that we find the smallest element from the entire unsorted array, and we put that on the leftmost side of the list. And that smallest element becomes part of the sorted array. And we keep on repeating this until we sort all of the elements array from right to left. This also is not suitable for large data sets because it scales horribly. And the average and worst case complexities for these are going to be O of n squared. So you try to use selection sort for very small data sets. So let's visually see how this actually works. So we can start back with our unsorted array here. And we check the entire list here, or entire array here, for our smallest value. So in this particular case, the smallest value here is going to be 10. When we find the smallest value here of 10, we move this value from where it is to the leftmost value in the array by doing a swap here accordingly. So we swap this smallest value with the leftmost value here, such that the smallest value is going to be on the left-hand side of the array. Because that smallest value here is considered to be our sorted array, the remaining contents here are our unsorted array. So we're going to be searching the unsorted array for the next possible smallest value. So we start with 33 here, being the start of our unsorted array, and we go through each one of these values here to find the next smallest possible value. Find that 14 here is the next smallest value. So for the unsorted array here, we swap the leftmost value here for the unsorted array with the smallest value in the unsorted array here. And when we do the swap, these two values here will be in order, and those will be also forming our sorted array accordingly. We keep on repeating the processes here until the rightmost part, being our unsorted array, is reduced, and the leftmost part, being our sorted array, grows accordingly, and we end up getting the entire array sorted from least value to highest value. So the algorithm for the selection sort, is given here for your reference. And the code for the sorted of selection sort is also given here. It's also provided for you guys on my learning such. Alright. So physically we can see here that selection sort may be a little bit more advantageous than insertion sort because it goes through the entire array and it makes sure that for each instance when we are populating the sorted part of the array from the unsorted part, that the values line up in particular order from lowest to highest. We also see that for insertion sort, there were some repeated steps of multiple swapping between values, which may be unwanted in particular cases. So we can see that selection sort may be a better candidate than insertion sort. The question I'm posing to you guys to think about here is, where would insertion sort be better than selection sort? So that's something for you guys to think about. Are there any particular questions on selection sort? Alright, doesn't seem like we have any questions on selection sort. Right, let's move on to the last sorting that we want to do today, which is bubble sort. So bubble sort is basically a comparison-based algorithm where we just basically check each adjacent element, meaning the elements next to each other, and we swap them accordingly if they're not in order. And bubble sort is also not suitable for large data sets. It's also suitable for small data sets. The average and worst case complexity is then going to be O of n squared, because that means you end up going through the entire data set twice. No, the selection sort doesn't have to be optimized. That actually is the most optimized version of the selection sort that you have. So that's a good way it is there. The insertion sort is not optimized. The selection sort there is actually pretty optimized. So there's no other way for you to optimize that selection sort. So bubble sort here is basically a comparison base. It's also not suitable for large data sets. The average and worst case complexity is going to be O of n squared. And we're going to physically see and visually see how it actually operates here in the next few slides. So we can start with any unsorted array here. And we start with the very first two elements on the left-hand side, and we try to figure out which one is going to be the greater value. So we start with the first two elements being 14 and 33 here. We see 33 is going to be greater than 14, and it's already in its sorted location, so we don't need to bother with these. We then move on to the next two values being 33 and 27, and we see that 33 here is greater than 27, or the controversy being 27 is smaller than 33, so they're not in order here. So we swap these accordingly for it to end up being in order as of such. We then compare the next two values to see which one is going to be smaller, which one is going to be larger. And we can see here that 33 is less than 35. So these are actually in order, so we don't need to do any swaps here. And then we go on to the last two values, and we see 35 here is greater than 10. So then we swap these accordingly as of such. Now, the array after this first iteration and all these swap-ins looks like this. We then have to repeat all those swap-ins again for the array again to make sure that the array ends up being sorted from lowest to highest value. So for the second iteration of the array, we repeat all those steps again, and the end result ends up looking like this for the second iteration. The third iteration, it looks like this. And then for the fourth iteration, it looks like this. And for each iteration, you can see basically that the right-hand side here, we end up getting all values being sorted in the correct order. When there are no more swaps required, meaning that no swaps are required for any iteration, the bubble sort algorithm knows that the array is completely sorted. So I'm repeating that. So long as there are no swaps for any particular iteration, bubble sort knows that the array is completely sorted. The algorithm for bubble sort is given here. Your swap function is also given to you guys in your C++ code, and the bubble sort algorithm is also written in C++ code, and it's posted on my learning for you guys to actually see how it operates. The code is also here on the slides for quick reference, see how it operates as well. Note that our swap function here uses pointers. We don't use raw values, we use pointers for our swaps. Alright, so that brings us to the end of our first sorting and insertion algorithms lecture, where we saw insertion, bubble, and selection sort. And we've noted that each one of those were not very suitable for large data sets. And all of them basically had average and worst case complexities of O of n squared, meaning that we'll have to end up going through the entire array twice in some particular form or fashion. The code for bubble sort, because I know it may end up being asked, that is also an optimized version of bubble sort. There is probably no further way to optimize that. So you don't have to worry about that too much. In next week's Monday lecture, we'll be going with merge sort, quick sort, and bucket sort, which will bring us to the end of our sorting algorithms. And we'll also be learning about one searching algorithm, which tends to be the most popular searching algorithm and probably one of the most simplest ones to learn, which is going to be our binary search algorithm. All right. So are there any particular questions regarding the material for sorting and searching algorithms in this particular lecture? Yes, the reason why you use pointers for your swaps is that because when you use pointers, it's actually what we refer to as a true swap. If you use raw values, what happens is that you just end up copying the values and you don't actually swap the values. It becomes like if you're copying the values so they get their own, how to explain this? Okay, so if you copy those values, the copies are allocated to new memory locations. And all you just do there is that you just switch those new memory locations out of such. You end up using double memory. The reason why I use pointers is that you can use the same memory without using double the amount of memory. So the pointers there allow you for it to swap accordingly using the same memory locations that you started with to begin with. The code for insertion, bubble, and selection sort is basically standard syntax that you will need to memorize for any programming interview. And in some cases, yes, you will have to modify the inputs and variables, but these operations are going to remain the same no matter what. So the same sequence of steps for the sorting will be the same thing no matter what, depending if you change the inputs or if you change the variables, or if it's going to be a different programming language, it's going to be the same instructions and the same sequence. So yes, it is the same standard structure and the standard syntax for our C++. Right. Any more questions in particular? The structure will change very slightly. Very slightly. It won't change much. But if you go into an interview, you can actually use that structure and you will be able to get away with that structure. Because the interview, they don't expect you to know the most optimized versions of any sort of code whatsoever. They do expect you to have unoptimized ways of doing things, and because it's limited time. They just want to see how you go about doing your thought process. So how you approach the problem, what reasoning you take, what assumptions you may make, those sort of things that are what they're going to be looking at. You don't have to write the most optimized code for any sort of programming interview. So long as the code is functional and it can work in theory, they're perfectly fine with that. What they are looking for is your logical explanation and reasoning. Alright, so doesn't seem like we have any further particular questions regarding our material here. So that brings us to the end of our lectures for the week, actually. And Wednesday's session would be just basically sort of any review that you guys need regarding preparation for your quiz or for your group assignment in particular. So once I close off this session here, expect a forum post pretty soon, giving you guys details of what your quiz is going to be like and what your group assignment is also going to be like, with your types of questions that you will encounter, the structure, how much time you will have, the amount of attempts, formatting, all those particular details and so forth. You will get that in the forum post. And feel free to ask any questions on the forum post as well, in case there's something you need a little more explanation with, you think that you need to rectify and so forth. Feel free to ask at that point, because we still have time before any of the quizzes or group assignments actually go live regarding this. So feel free to ask at that point. Regarding the material of today's lectures, feel free to leave any questions down in the comments below, or you can directly email me. I'll respond to you guys accordingly as such. But until then, and well, I guess until Wednesday, for any practice or resolvements that we have in that hour session, take care, safe. I will see you guys soon. All right, later.